So we have exactly noon now, so we shall start. Hi, everyone. It's my pleasure to welcome you to the session dealing with microarchitectural effects. And our first talk will be given by Yannick Zeidner from University Bochum, and is entitled Preload SW, Probing-Based Software Leakage Detection for Binaries.
Hi everyone. Welcome to this talk about ProLite software.
Yes.
Perfectly. Which is a joint work with Nikolai Müller and my supervisor, Amir Moradi. So a couple of decades ago, smart people came up with algorithms of encryption schemes we all assume are pretty much bulletproof. They have mathematical properties we understand quite well and were also thoroughly evaluated. However, at least since the discovery of side channel attacks, this security started to show some cracks. We discovered that undesired side effects, such as power or timing, can reveal secret information and thus bypass the security of the underlying algorithm. This is not only a threat for hardware implementations, but also for software, which is the main focus here in this talk. Luckily, we can regain the security by adding countermeasures. And the most common countermeasure is masking, based on the principle of secret sharing and commonly applied on the algorithmic level. Here, we split a secret variable into multiple shares, which are uniformly distributed. And then when we perform the computations on those randomized intermediate values, it breaks the dependency between the power consumption and the original variable. Now, when I started in the field of software masking, I was amazed by the number of provable secure masking schemes, and I thought we're on a really good way. Unfortunately, it shows that when practically evaluating those theoretically secure schemes, they often cannot uphold their security in practice. So we clearly see a gap between theory and practice, and this is what motivates here our work. And this is mainly due to two reasons. First of all, oftentimes those proofs do not consider microarchitectural effects. And second of all, the adversary model does not resemble the real world close enough. So we see a clear gap, and this gap is particularly large in software as we face multiple challenges. The first challenge is already the abstraction level. Usually software developers write their software in a high-level language, which then gets compiled to a binary. Now, during this compilation, the compiler might reorder or optimize, which might lead to unintended recombination of shares, which is then followed by further pitfalls of the underlying hardware. Next up, software developers usually do not have the netlist available. Thus, they have no insight what actual microarchitectural effects exist, or are even completely unaware that such exists in the first place. Now, I think most of you would agree that verification to check if the software you wrote is actually secure in the presence of such microarchitectural effects would come in very handy. Unfortunately, here we face another challenge, which is the nature of software. Compared to hardware implementations, software implementations usually have a large number of instructions and clock cycles. This makes formal verification not really scalable because they have to perform an exhaustive evaluation and, to be precise, also require the underlying netlist. Furthermore, formal verification on netlists, here current research indicates that this is tightly bound to the netlist you're evaluating on. And this is because vendors might have different RTLs, which then get synthesized differently, which will eventually end up in a different microcontroller. And furthermore, we have a more practical challenge here, which is if you perform some leakage assessment and identify leakage, then it's really hard to trace the root cause of the problem. So often what you would have to do is you would have to reverse which instruction was executed, for example, during this leakage measurement point. And this is very tedious, especially when you have many leakage points, and also consumes a lot of manpower. So here we present ProLite to tackle these challenges. And ProLite software comes with two major contributions here. First of all, we introduce a CPU-independent leakage model, which operates on a generalized and potentially conservative CPU, which explicitly incorporates multiple microarchitectural effects known from public literature. Now, this leakage model is now the baseline for our tool, ProLite software, which performs a simulation-based verification under this model on your binary. ProLite software itself comes with multiple advantages. First of all, we are able to analyze arbitrary orders in a univariate and multivariate setting. Next of all, we put almost no restrictions on the software you want to evaluate. So for example, your software can have branches, conditions, nested function calls, recursions, and even we're able to verify non-constant time code. Next up, we do not require any netlist because we're operating on our generalized CPU. This makes it not only easier for software developers, but allows a more generalized statement about security under the different microarchitectural effects. The microarchitectural effects themselves can be freely combined, which is not only handy in situations where you have higher order adversaries, but also in situations where transitions and glitches inside the CPU can occur simultaneously. With ProLite software, we are able to evaluate large implementations efficiently and provide a detailed report which pinpoints the root cause of the instruction, which means it gives you an explanation what microarchitectural leakage caused, which microarchitectural effect caused the leakage, which instruction, which register, and potentially also which bit position. Now, before we dive into ProLite software in detail, let's have a more high-level overview at first. ProLite software analyzes binaries, so you of course have to provide the binary itself, followed by a configuration file which contains all meta information about the simulation and also what kind of microarchitectural effects you want to consider. We also give the user the opportunity to just provide the source and linker files and let ProLite software internally compile the binary. In this case, you would have to specify the compiler flags in the configuration file as well. Now, ProLite software internally consists of three major steps. First of all, it takes this simulation and it takes the binary and performs the simulation. And during the simulation, it places the user-specified probes. Then it will take those probes and groups them into a probing set. And finally, this probing set will then be used for statistical evaluation. ProLite software incrementally outputs a report which specifies if it's identified leakage and also traces the root cause of the leakage if leakage exists. Now, to understand what information the adversary can gain with different microarchitectural effects, let's have a look at how our CPU model looks like. And first of all, here we would like to note that we consider ARM binaries. So our CPU has a register-register architecture, meaning that values have to be loaded into register first before they can be used. So they cannot operate directly from memory. All general purpose registers are stored in a register file, and each general purpose register has capital B bits. Next up, we have a memory area M, which is accessible via different memory addresses MI, and the accessible size is either byte, half word, or word size. Now, between the memory and the register file, there is a load and a store bus. Next up, we have the ALU, which performs all the Boolean and arithmetic operations. And finally, we have a pipeline with n stages where n can be freely configured by the user. Now, with this model in mind, let's have a look at what kind of microarchitectural effects we can derive from here. And the first one and simple one are transitions. And transitions are pretty similar to the ones we already know from hardware. They occur across different instructions and are so-called inter-instruction leakages and give the adversary joint information about the old and new value inside storage elements. Now, here it's important to note that we do not only consider transitions inside general purpose registers of the register file, but also transitions and overrides inside the memory. And transitions inside the memory are then called memory overrides. Next up, multiple publications have also indicated that consecutive memory operations between different memory addresses can also lead to joint leakage of information. And this is not clearly apparent here in our initial model, so we have to apply some adaptations. And what we do here is we introduce shadow registers on the load and the store bus. Now, regardless of the memory address, if we are loading or storing a value, this value will go through the shadow register. And now it's more clear why we can observe joint leakage of information between consecutive memory addresses as transitions apply on this shadow register as well. We also specify this memory shadow register a bit more by saying that the shadow register always contains the full word size value. And this is regardless of the size of the mnemonic. So regardless if we are loading a byte or loading a half word, the shadow register will always contain a full 32-bit value. Next up, we consider microarchitectural effects inside the ALU. And so far, each bit leaked the information independently, but this is not the case inside the ALU because we model our ALU as always active, which means that the ALU performs multiple operations in parallel and only forwards the correct result of the instruction to later pipeline stages. Now, besides bitwise operations, such as XOR, ANDs, and ORs, we also have non-bitwise operations inside the ALU, such as shifts, adds, and subs. And those operations can combine multiple bits inside the same register, and this is exactly what we model with the horizontal probe. We further specify this effect a bit more by observing that we do not only have one source register inside the ALU, but two source registers. So we also allow an horizontal probe to have a pairwise observation of horizontal effects within one probe. So for example, if we place a probe at the output of our multiplexer here, this will propagate back to an operation, and we can see here that the operations are connected to both of the source registers. Now, next up, we define vertical probes, and vertical probes occur during the decoding stage. And what happens here in the decoding stage is that the CPU selects the registers that will be afterwards sent to the ALU for the operations. And this register selection is based on addresses from the decoding stage and its underlying combinatorial logic. Now, we know from hardware that combinatorial logic is susceptible to glitches, and this is exactly what we model here. Due to glitches in the decoding stage, the adversary can gain information between seemingly unrelated registers. We also specify this vertical probe and this vertical effect in two ways. So we have two variants. To get reasonable results fast, we allow the pairwise combination of registers. So for example, if we place a probe on the first bit of the output of the multiplexer, this will then propagate back to the pairwise observation of the first bit of registers. And more generally, we allow the observation of the ETH bit of all registers within one vertical probe. So for example, if we place the probe on the first bit of the output of the multiplexer, this can also affect all the first bits inside the register file. Now for our last effect, we have a look at the pipeline. And pipelines are usually implemented inside CPUs to increase the efficiency, but pipelines themselves can have also some optimizations. And one of the optimizations here, for example, is pipeline forwarding, where the value from later pipeline stages can be forwarded to the ALU before they're actually written back inside the registers in the register file. Now, when we want to forward the values from later stages back to the ALU, this requires some combinatorial logic. And as we've seen before, combinatorial logic is susceptible to glitches. And this is exactly what we model here. And as before, we also model this very conservatively by saying that an adversary has access to the ETH bit of the full register content of the last n instructions, where n is again the configurable pipeline depth configurable by the user. Now, after we've seen what microarchitectural probes we can get and what our CPU model looks like, ProLite starts to simulate the binary. And therefore, it will generate the input based on the user-defined groups. So for example, fixed versus random, fixed versus fixed, but it can be any group and any number of groups. And then with those inputs, ProLite will start to simulate your binary. During the simulation, ProLite will create probes whenever the content of a register or memory changes, according to the user-specified probes. Now, after a simulation, we have those loose probes, and ProLite will then group those loose probes into a set of related probes, so-called probing set. And the probing set is the ability of an adversary. So for example, if we have a second-order adversary, he can combine two microarchitectural probes within one probing set. So for example, let us consider 3 probes per instruction during the simulation and 2 instructions in total. Now, a univariate adversary can combine 2 probes within the same instruction, which gives us in total 6 combinations. And a multivariate adversary has all univariate combinations, but is also able to combine 2 probes between different instructions. So this gives him in total 15 combinations. Now, after we generated the probing set, ProLite will translate the microarchitectural probes in the probing set into standard probes. And this procedure is important because it's required for the statistical analysis later. So what I mean by this here, for example, let's consider still a second order adversary, and we have the two microarchitectural probes where one probe is the horizontal probe on R3, and the second probe is the second bit of the shadow register. When we translate it into standard probes, we get information about all bits inside the register of R3 and the second bit of the memory shadow register. Next up, the final representation of the last slide was required to perform the statistical analysis. And here we follow the procedure of the hardware very close. So where we use statistical evaluation to check if we can identify significant dependency between different groups. So for example, between a fixed or a random group, a fixed and a fixed group, but it also can be any other amount of group. And what we say here is our initial assumption is that there should be no relation between those groups. And this is exactly here what our null hypothesis states. Now, based on our result of the hypothesis test and based on the computed p-value, we then either accept or reject our null hypothesis. Like in the hardware version, we use the g-test of independence for our statistical analysis. And we do this because it's not bounded by any statistical moment, but rather considers the full distribution table of each probing set. Now, we evaluated ProLite on several publicly available designs. We did not only focus here on full rounds of masked ciphers, but also considered permutations and conversions between masking domains. For all of the experiments, we set the maximum number of simulations to 10,000 and implemented ProLite in such a way that different effects were selectable. So you can really choose which effect you want to have a look at and which not. As you can see here on our table, on our result table, we are able with ProLite to evaluate software with over 100,000 instructions and found several mistakes that either lead to detectable leakage or violated security claims by the authors. Here, I would like to note that some schemes were already modified by the authors, and also most notably, maybe some of you attended the talk previously, we also found a bug in one of the implementations of the best paper that was presented previously. And here I would like to note that this is not a flaw in the scheme itself, but it's rather a non-trivial bug in the implementation. And it shows how hard it is to follow security principles in software. And with this, I would like to further emphasize the usage of our tool. Now, to conclude, what we did here in our talk and in our work is we presented two things. First of all, we presented a CPU-independent leakage model, which explicitly incorporates multiple microarchitectural effects, and then used this model for ProLite software, which is a simulation-based tool to evaluate the probing security of binaries. We're able to evaluate large designs and do not require any heuristics, as our statistical analysis is based on the actual intermediate values. Right now, we are limited to ARM architectures, but our general approach is easily extendable to other architectures, for example, RISC-V. What we want to highlight here one more time is that we almost put no restrictions on the binary you want to evaluate. So you have a lot of freedom to implement the binary you want. Unfortunately, the drawback of ProLite here is that the results of ProLite cannot be considered a hard proof because we're operating on our generalized CPU and the behavior on an actual microcontroller might differ. However, if you like this talk and if you would like this presentation and also, of course, the tool, you can check it out publicly. It's publicly available on GitHub. If you want to play around with it, yeah, go for it. And with that being said, I conclude my talk and thank you for your attention.
Thank you very much for your talk. We have a question here.
Hi, thanks for the talk. You're not considering cache timing attacks in your ProLite. Would it be possible to simulate that?
Sorry, cache timing attacks?
Yes.
No, we do not consider timing attacks in general. I actually thought about it, and I think it might be extendable, but I don't think that we, for now, plan to implement it in ProLite.
All right, thank you.
Do you consider leakage in the control path?
I'm sorry, what?
In the control path of the processor?
I'm not sure. I mean, if the control path behaves similarly to the effects we modeled, then it might be the case, but we did not have an explicit look into that.
So you modeled your memory accesses with a shadow register. Some CPUs don't have just one register, but multiples. How hard is it to extend that, and how do you actually define the model? So is it a text file, or what form of model, or how do you write it down?
So the first question was about the shadow register, and what we have is we implemented a simulator, and there we just added a line which contains just a 32-bit value, and it's just a 32-bit variable, and you can easily extend or add another variable to the implementation of the simulator. So it's easily extendable to have a higher depth of shadow register, for example. The second question you would have to repeat because I forgot.
So how do you specify that? Is it a text file, like your CPU model?
So on our configuration file, we have some acronyms, and you can just say, okay, transitions, yes, no, for example. And you can also say, for example, horizontal effect by saying HR, which means horizontal effect, and then you can just consider it. So it's just a switch on and off. It's hopefully designed to be very easy to select which effects you want to consider.
Still have a question here.
About the glitch effect, how did you simulate this?
That's a good question. We simulated the glitches by observing the change of the register content, because when we detect changes inside the registers, we apply the vertical and the horizontal probes. And this is also a indirect way to simulate the glitches. Maybe we can have a discussion after that, because I think it's a bit more complicated, and with the design it would be easier.
Okay, thank you.
So I noticed you considered the ARM architecture. So the question I would have, I would assume the baseline RISC-V architecture would have similar, if you wrote a simulator for RISC-V. However, there's a lot of extensions to RISC-V, and I would assume also potentially as you add more and more instructions, it becomes harder to produce a ProLite, for complicated RISC-V architecture. So how scalable do you foresee this in the context of RISC-V?
I'm not too familiar with RISC-V. I'm just saying I, for example, extended the ARM simulator to have also the V7E extension, so the DSP instructions, which was around, I don't know, 100 instructions. And it was relatively easy to add those instructions. I mean, it took like two or 3 days. So if you have the baseline of the simulator, then I think it's easy to add the instructions. But maybe one thing, if you have, for example, also the netlist available, then maybe other tools could also work where you don't have that much overhead. Yeah.
So the ARM has, in addition to the ALU, also all these shift operations that can happen. Are these also simulated, all possible shifts when you look at the glitches, because that looks like quite a lot of combinations?
Yes, it is a lot of combinations, but the shifts were already included with the horizontal probe, where we contain all the information of the shifts into one probe. So we have all the information of the bits. And also with the pairwise horizontal probe, we allow also more substantiate information about the adversary.
Okay.
I think the time is down for questions, but you can, of course, go to talk to Yannick over lunch if you want for further discussions. So let's thank our speaker again. And now let's welcome let's welcome Florian Stolz, who is going to talk about risky translation, securing TLBs against timing side channels.
Thank you. Okay, yeah. Welcome everybody to my talk about our paper, Risky Translation, Securing Translation Local Side Buffers against Timing Side Channels. And this has been a joint work by Jan-Philipp Thoma, Pascal Sotzlich-Timgenesio, and myself at the Ruhr University Bochum. So let's start with a bit of motivation. And of course, it should be no news to you that modern CPUs are running multiple applications at once. However, in order to do this, we need to solve some problems. First of all, problems may have different RAM requirements, some much, some not so much. And of course, they should run in isolation because as you see in this example, if you have two programs, they both have data at the physical address 42 and they access it, then of course you get some problems. So that's why modern CPUs all usually have a memory management unit, and this handles memory abstraction. And the way it works is that now every program gets a virtual address space, so each program can have the address 42. However, inside they are translated to completely different physical addresses. So now we just need a management scheme, and to keep a long story short, we had many different approaches, for example, segmentation, but ultimately paging won. And paging works like this. So you have your physical memory, you split it up into frames. Each frame can hold exactly one page. A page refers to 4 kilobytes of data, but you nowadays can also have more. And then we have a small page table which keeps track of what virtual addresses correspond to what physical address. However, if we have to look into this page table all the time, that will of course be very slow because we have to do memory accesses and so on and so forth. And that's why all MMUs usually have a translation local side buffer, or short TLB. And this is just a cache which keeps the most recently used translations close to the MMU, so we get it faster. So a cache is just a highly efficient piece of memory closely located to the CPU, or in our case, the MMU. And it can provide us with data much faster than if we have to request it from main memory. And to do this, they usually have a special structure, usually set associativity, and it works like this, as you can see in this example. We have a memory address and we split it into a tag and an index, and then the index basically selects a raw, and then in our example here, we have 4 possible locations where the data might be. However, I mean, caches are great for performance, but they can also introduce security issues, and that's just because some caches might be shared between programs, and naturally you might have a victim and an attacker, and the attacker wants to extract information about the victim. And the most relevant attack for this paper is the prime and probe attack, but there are many more. And the prime and probe attack works like this. So under the assumption that we know where the victim will place its data in the cache, we just generate some addresses of the form like this, and they all have the same index, and they all fall into one row. Then we let the victim execute, and then we just re-access our addresses again. And if there is any slowdown, then we know that the victim must have performed an access because some of our data is missing. And this can be used to extract crypto keys, for example, when you use square and multiply. Unfortunately, the very same is true for TLBs. It has been shown by Gras et al. In 2018. And the only real difference is that the information is more coarse-grained, but it was still enough to extract keys, for example, with square and multiply. Okay, so some of you are probably familiar with caches, and you might think, yeah, cache attacks, they are not so new. We have many countermeasures already. Can we just copy-paste them? And the short answer is yes. Previously, Deng et al. Investigated 2 countermeasures in relation to TLBs, and that was static partitioning and random fill. So static partitioning basically splits the TLB into 2 parts, a secure and unsecure part, and the random fill method just fills the TLB with random translations. And these are all good methods. However, what we found is that in a general purpose computing environment, they may not always provide the best performance security trade-off. So this leads us to TLB-Code, where we basically wanted to combine the strength of the two previous approaches, mainly separation of processes, which you naturally get by splitting the TLB, and also this randomness, which makes attacks much harder. At the same time, we wanted to fix some weaknesses. For example, static partitioning does not allow mutually untrusted secure applications to run at the same time. And also we wanted to keep the operating system modifications quite low. And we do this by employing index randomization, which is a well-known cache countermeasure. However, we did some adaptations so that it works very well in the context of TLBs. So how does this work, or randomization in general? So now maybe you remember the picture from before. We had a tag and an index. Well, now the index part is completely gone, and we just throw the tag into a randomization function. In our case, this is a free-round prints because we need a very low latency function. And this will give us an index for each way, and thus the static structure of set associativity is broken up, and we successfully prevent prime and probe. Unfortunately for us, clever people found a more specialized version called prime, prune, and probe, which works for randomized caches. And here the attacker basically tries to profile this randomized mapping, and with enough time and addresses, he will find collisions with the victim, and then he can just do the same stuff again like before. So how can we fix this situation? So the first problem is that the attacker and the victim, they share exactly the same mapping function. And on modern architectures, we can break this up very easily by including the process context identifier on x68, or on RISC-V, the address space identifier. And this is just a unique number assigned to each process. And we just append it to the key, and thus now the attacker and the victim, they don't have exactly the same key anymore. So the mapping will be different and it will be harder. However, with enough time and many, many addresses, the attacker can still find addresses. So how do we solve this? Well, we just don't give the attacker enough time. And that's why we add a random ID for each process. And naturally, when we change the random ID, it changes the key and the mapping is different. And thus, if we do this occasionally, the attacker always has to start from scratch. He can't use any of his previous knowledge. Now the question becomes, when should we re-randomize? Because you really don't want to do this too often, because every time you do this, you basically lose all your data in the TLB for this process, and that will be very slow. And here we can abuse a very nice attribute of TLBs, and that's the very high hit rate. So when you think about, for example, functions or data, they are usually continuous. For example, a function, all the instructions are right behind each other. The branches are also very small. So when you access one page, you will most likely access the same page for quite some time. And we actually confirmed this by running some parsec benchmarks, and we found that the median miss to hit ratio is just 0.22%, so super low. And now the thing is, if you do prime, prune, and probe, you need all these addresses, and they will create misses, and you will do this very often. So our solution is to add a miss counter for each process. And anytime there's a miss, it will count down. And once we reach 0, we change the random ID and we re-randomize. Now, you might ask, what should the miss counter initial value be? And this depends on the replacement policy and the TLB size, which I will talk about in just one second. But just to give you a short conclusion already here, when you set the miss counter to the TLB size, you get the best performance security trade-off. So let's quickly talk about replacement policy, because that's not what so many people think about. Because when you use classic caches, you most likely use LRU, or least recently used. So when you need to replace an entry, you just take the oldest one. In this picture, it's represented by the red color, and you just throw it out and you update the ages within this row and you are done. However, when you do a randomization, this is not easily possible anymore, because now you don't do this age comparison in a row anymore, but anywhere. So the entries must be comparable to each other entry in the cache. So you need a very large timestamp, which becomes not feasible. So what could we do instead? And the first thing which came to our mind was to use random replacement, because it's very easy to implement. However, we ran a simulation on how many tries the attacker needs to find a collision. And there's this graphic here, which we did, and random replacement is at the top and LRU is right below it. And the box for random replacement is lower than for LRU, which indicates that it's actually easier for an attacker to find a collision if you use random replacement. And that's just because the attacker doesn't have to care about the age relation. So it would be very great if we could use something like LRU. So we came up with an approximation, which we coined RP-LRU, which stands for random pseudo LRU. And you can also see it in this picture here. It's below LRU. It's not as good, but much better than random replacement. So how does this work? So let's say we want to throw out an entry from the cache. So first of all, we need, of course, to use our randomization function to get the possible entries. And we extract them from the cache and we throw them into a comparator. Now the comparator will deliver us the least recently used element, which in our case is the red one. And then we just select the line, like in the classic LRU, and we perform LRU just in this raw. So as you can see, this is not true LRU because we should have updated the ages of the selected entries, but we only did it in the raw. And this is a good approximation, and it gives and it's actually feasible to implement in hardware. So let's talk a bit about security and performance of TLB-Code. And in order to evaluate TLB-Code, we implemented it in two ways. First of all, in GEM 5, this is a state-of-the-art computer architecture simulator. And here we basically performed a simulation of a full Linux environment on a simulated RISC-V 64-bit board. And then we also wrote a standalone cache simulator. And this just does a functional simulation. And this is very nice because it's noise-free and it gives us access to important data like replacement candidates. And so we can perform a really in-depth security analysis. So maybe you remember prime and probe, which started all of this. So of course, TLB-Code should protect against prime and probe. And in order to determine this, we performed a fixed versus fixed t-test. We wanted to find out if the victim either performs an access in the eviction set. The eviction set is just a set of addresses which collide with the victim, or if it doesn't do it. And basically, for a standard TLB, we confirmed the results from Grass et al., which was not so surprising. As you can see in the graph, we quickly rise above the threshold of 4.5, which usually indicates leakage. However, when we apply TLB-Code, we never reach such significant leakage just because the placement of the victim becomes unpredictable. And even if you have an eviction set at the beginning, it will fall apart because of the re-randomization kicking in. Okay, so prime and probe is all well, but maybe you also remember prime, prune, and probe. So here the attacker wanted to profile the mapping. And so the success condition for the attacker is that he can profile the mapping before the re-randomization kicks in, because in this time he can actually extract useful information. So in order to do this, we ran our functional simulator, and most importantly, we gave the attacker two additional pieces of information. First of all, is the eviction set he's building actually functional? So is there any collision? And is the victim in the cache or in the TLB? And normally, this information is not available to the attacker and must be accessed, must be determined via more accesses to the TLB. And so our simulation is basically a best case scenario for a very lucky attacker. So our first simulation was pick a random range of address in a specific size and no re-randomization is applied. And this is what you can see in this graph, where the red line represents the success probability and the blue line, the average misses. And naturally, the more addresses you choose, the more successful you are. But what you should also notice is that the miss curve is exponential. And this is, of course, not very good for the attacker. So if he uses a priming set size of 60, he will quickly rise over a threshold, and that's no good. So this creates a situation for the attacker where he would like to use a large set, but he can't. So he needs to trade success probability for misses. And we confirmed this by rerunning the experiment now with re-randomization enabled. This is the new graphic which just popped up, and here you can see the red line represents the threshold. In our case, it was 64 because it was a TLB which can hold 64 entries. The blue line represents the minimum amount of misses we ever observed, and the green line represents the successes. And so it confirms our hypothesis. Now the attacker chooses a small priming set, so only 24 addresses, because this generates the minimum amount of misses to stay under the threshold. However, what is probably not seenable here, but you can check out in the paper, after 100,000 attempts, he only was successful in less than 20 times. And what you should also remember from before is that I said that this is the best case scenario where the attacker has additional information which is not available in the real world. So if you add this, that he has to do this more accesses to get like the information about the functionality, and if the victim is in the TLB, then the attack becomes unfeasible. So let's also talk about performance. For this, we measured the miss to hit ratio using Parsec. And just because when you create more misses, of course, the performance will go down. So here we compared a standard TLB-Code with our replacement policy, and TLB-Code with a ideal LRU policy. But as I said, it's not feasible. And what you should observe here is that we are not so much worse than a standard TLB, and that RP-LRU is also a good approximation for LRU. And what is also noticeable is that, for example, for black scholars, we were actually better than the standard TLB. And that's just because that in a set associative cache, there might be some unfavorable access patterns, which just don't exist once you add the randomization. Okay, so let's talk a bit about hardware. And for this, we implemented a TLB and synthesized it using the Vacus 15 nanometer library. And what you should see here is that the ways take the most space. But the good thing for us is that the ways are always so big because they are the storage elements. We don't touch them. They always store the translations. So everything we add is basically around the ways. And it's also a very feasible overhead. And now what is also important is that the TLB is in the critical path of the CPU, because when you do a L1 cache access, you actually have to do a TLB lookup. So if we are very slow, that's of course no good. And so we measured just a critical path delay of 0.143 nanoseconds for the TLB-Code module. And this is well within the range which is observed on Intel CPUs. Okay, so to sum up, what you should take away from this talk is that the TLBs are they are vulnerable for timing side channels, and that, for example, TLB-Code can protect against them using index randomization. Our method only uses minimal operating system modifications. We only need this additional miss counter and the random ID, which must be saved on the context switch. And as I just explained, the hardware overhead does also not significantly impact the operation of the CPU. So I'd like to thank you, and do you have any questions?
We have here a question from Don.
Thanks for the nice talk. I was wondering, how do you handle shared memory?
Shared memory.
Mm-hmm.
So with shared memory, then you would have to place 2 entries into the TLB, because that's not possible.
Yeah, so you deduplicate those. Okay.
Yeah.
You duplicate those. And then I had another question on the replacement policy.
Yeah.
So it has some LRU left, so that's stateful. Have you checked whether there is any leakage in the replacement policy that an attacker could potentially exploit?
No, unfortunately, we didn't check for leakage in the replacement policy, but thanks for the hint. We will have a look.
Yeah, okay, super, thank you.
Maybe I can ask a question. So how do you envision your defense combined with others to give a complete protection? Like, would you still need to protect other microarchitectural components? What would you need to do in software?
Yeah, so it should be combined with other defenses. So, for example, this just protects the TLB. So if the normal cache is still there, we have seen it's vulnerable. So you would have to, protect against also cache attacks. And but for TLBs, it would significantly lower the like software countermeasures, because the operating system, or basically the hardware, handles all the things for the TLB, so you don't have to worry anymore about the translations.
Yeah, I was, oh, there is one here.
Yeah, in your paper, you reported 1.6 nanoseconds for the 45 nanometer technology, and then it's 11x smaller, approximately, the 0.143 nanoseconds for 15 nanometer. So my question is, did you do place and route and include all the parasitic capacitances? Because that'll affect the delay significantly. Or did you use estimates from synthesis?
No, we just synthesized the TLB module with our modifications. We didn't model any capacitors.
Yeah, following up on my previous question, I was wondering also if, like, the store to load forwarding could leak something about the addresses that you would also need to consider in the microarchitecture.
So I'm not so deep into the CPU architecture that I can make a clear comment on load forwarding, but if there is a TLB access which must be done to do this, then our countermeasure would secure against it. Or did I understand was it your question? Or?
Yeah, well, I guess if you just allow code software to branch on secrets, you would also need to secure the store to load forwarding, or to consider that it may leak things if you can forward or if you can't forward. No, I don't know. No, that's just a thought. Okay, then if there are no more questions, maybe we can go for lunch. Thank you very much. And